Okay, so I'm going to answer just a couple questions that came from Calc 3 student from the homework and or prep. So this section 13.3, we're talking about partial derivatives. And the idea behind a partial derivative is that you keep one of the variables, or all, I should say, all but one variable you keep as constant. So you think about them as like a six, just a number. And then you take the derivative with respect to the one variable that you're not thinking about as constant. And the notation for second derivatives is a little cumbersome. There's a shorthand notation which is not so cumbersome, but I see in most of these problems they're using like the cumbersome notation. So let me just show you what that means. So let me get a pen here. So if we wanted the partial derivative of a function with respect to x, what this means is pretend all the other variables are constant. So pretend all other variables besides x which is told by the bottom there. So besides x are constant. So if your function has two variables, if your function's f of x and y, well, then we would pretend all the y's are just values. And what this is doing is if we fix y as a constant value, and it's easiest to visualize in the 3D plane. So if we've got our 3D plane here, right, this is your y, this is your x, and this is your z. And z is f of x, y. Then our function f of x, y is going to draw some surface in the third dimension, right? Now it's going to be a thin surface, but it can be curved and everything. So when we hold one of our variables as a constant, so not f, let's let y equal some value y0, then wherever, this point, x0, y0, we're going to like slice with a plane. So remember, y equals y0 or y equals 5, you can think of it like that, is a plane in 3 dimensions. So in 2 dimensions, it's a line, but in 3 dimensions, it's a plane. And this plane is going to intersect the surface at a curve. And so the intersection of the curve or of the surface and the plane is called a trace. And when we're finding the partial derivative with respect to x, we're finding the change in z or the change in f with respect to x. So we're finding the slope of the tangent line when y is fixed. So we're like literally just going to take like a tangent line on the trace curve. That's why we're setting the variables, all the variables except for the one that we're taking the derivative with respect to, as constants. And that way we're like picturing just a smooth curve of an intersection of a plane and a surface. So now if you wanted, so just to clarify, if we wanted the partial derivative of f, sorry, there's a plane behind me, I guess, in the air. If we wanted the partial derivative of the function with respect to y, then we're going to let all the variables except y be constant. And we're going to treat them, when we do the derivative, we're going to treat them as constant. This is a little bit different than when you're in Calc 1 and you've got an equation that we can't make into a function, and we'll use implicit differentiation. This is different than implicit differentiation because here we're not saying y is changing, we're saying let's fix y, or in this case, let's fix x. Okay, so now what if I wanted to take the derivative twice? So let's do second derivatives. Derivatives. Sorry, spelling doesn't count. All right, so if you want to do a second derivative, you have to do the first partial derivative first and then take a partial derivative after. So if, let's say I wanted to do df dx, so I want to take the partial derivative of the function with respect to x first, and then after I do that, I want to take the partial derivative of this thing with respect to, say, x again. So this, I would be doing the partial derivative of x, of f with respect to x. It's a mouthful, definitely. So I do the partial derivative of f with respect to x first, and then whatever I got, I would do, in this case, the partial derivative of that with respect to x. So now if you look at this notation, see on top there's a derivative and then f. So we write that as d2f. And then on bottom, you've got a dx and a dx, so we'll write that as dx squared. And that notation is bad because you're really squaring, or you can really think of the dx as squared, but they generally just put the squared right next to the x. Okay, so now the shorthand notation, which is really, really lovely in this case, is f, and then we'll put subscripts. So the first thing we did was the derivative with respect to x, so we'll put a little x. And then the second we did was x again, so we'll put another little x. So if you see d dx of df dx, that, or you see d2f over dx2, that means f sub xx. So the first partial derivative with respect to x, and then the second with respect to x again. So these guys go in order: first, second. Now, since there's two variables, we can actually do this 4 different ways. So another way that we could have done this was first take that partial derivative with respect to x, and then take the partial derivative of that with respect to y. So if we have on bottom or on top the d and then the df, that we would call that d2f. And then on bottom we've got dy dx, so we'll do dy dx. Now again, for shorthand, what did we do first? So first we did the partial with respect to x, so I write f sub x, and then second with respect to y, so I'll put the y second. And when you have the shorthand notation, it tells you which one to do first. If you have the kind of cumbersome d2f notation, you do these guys backwards. So you do first dx and then second dy. So now the other option was that we took the derivative with respect to y first. So df dy, and then after we do that first, then we do the next derivative, say with respect to x. So if we were going to put this in the d notation, it would be d2f over dx dy, and we're using not a regular d but a delta d. You can write as you could write it kind of looking like a d, but try to make it a little bit different than like a Roman d. Okay, so then this would be f sub, we did y first and x second. And then lastly, if we do the derivative of f with respect to y first, and then after that do the derivative of that thing with respect to y again, then we would have the d2f dy2 notation, or dy. And if we write that in the f notation, it would be f sub y. So the first thing with the partial derivatives is first learning how to take a partial derivative, and then the second thing is like being able to read the notation. Okay, so keep that in mind. Let me give you like a very basic function to take the partial derivatives of, just so you can see how it works, before I do these two examples which were asked through email, which are a little bit more intense. Absolutely, they're a little bit more intense. So let me get I'm just going to make up a problem here. So let's say we've got f of xy, and that's going to be 3x squared y plus 6x cubed y to the fourth. Okay, so if I wanted the partial derivative of this with respect to x, I'm going to treat y as a number. So if I have, so I'm going to just rewrite my problem here so I can put arrows. So 3x squared y plus 6x cubed y to the fourth. So now if I want to take this derivative with respect to x, here on this first term, the 3 and the y are constant. So when I take the derivative, I'll have the 3 and the y, and then I'll just do the derivative of x squared with respect to x. So that would be 2x to the first. So this first term, when I'm taking the partial of f with respect to x, would be 3y times 2x, which makes 6xy. Normally you put the letters in alphabetical order. Doesn't actually matter, but just customarily. So now let's do this next one. So 6x cubed y to the fourth, the 6 and the y to the fourth are considered constants. So they will stay outside 6y to the fourth, and then I'll do the derivative of x cubed, which is 3x squared. So this second term is 18x squared y to the fourth. Now, if I wanted to take a second derivative, so this is f sub x. If I wanted to take a second derivative, let's say f sub xx, that's going to be the derivative of f with respect to x, which we just did in blue. And then we'll take the derivative of that thing with respect to x again. So I'm going to do the same process, since the bottom, or what we're taking the partial with respect to, is x, we're going to keep y as constants. So here, in this guy, the 6 and the y are constant, so they stay out front. And then I'll take the derivative of x, which is 1. And then for this next one, the 18 and the y to the fourth are constant, and I'll just take the derivative of x squared, which is 2x. So just to clean that up, I'd have 6y plus 36xy to the fourth. And this would be f sub xx, or the partial derivative with respect to x and then with respect to x again. Now, we could have done f sub xy at this point as well. So remember, that's taking the partial with respect to f, or the partial of f with respect to x, and then, right, that was my first. Then, once I do that, take the partial with respect to y. So I'm going to take my f sub x, right? I'm just going to write it over here again so I can reference it. So I had 6xy plus 18x squared y to the fourth. Okay, so now when you're taking a partial with respect to y, you're saying, okay, all my x's are counted as constants. So x equals a constant here. You can think of it like the number 2. So on the first term, the 6 and the x are constant. So by the constant rule from Calc 1, they just come down. And then the derivative of y with respect to y is 1. And then on this next term, the 18 and the x squared come down. And then we'll take the derivative of y to the 4th, which is 4y cubed. So to clean this guy up, I have 6x plus 18 times 4, that's what, 72? So 72x squared y cubed. So now we could do this again and start with the partial with respect to y, where again, we keep our y as a constant, and partial with respect to y, we keep our x as a constant, and we take the derivative with respect to y. So again, let me just give you this very quick basic example before I give you the longer example. So if I wanted f sub y, in this first term, the 3 and the x squared are constant, so 3x squared, and then we'll take the derivative of y with respect to y, which is 1 plus. And now here the 6x cubed stays, and the derivative of y to the 4th is 4y cubed. So the first derivative, or the partial derivative with respect to y, would be 3x squared plus 24x cubed y cubed. And we could do a second partial derivative with respect to x and with respect to y. So we'll do that just kind of quickly here. So if I wanted f sub y, I would take f sub y and I would do the partial with respect to y again. Now in this first term, 3x squared, there's no y attached to it. So that's like taking the derivative of 6, or of 100. It's a constant, so the derivative is 0 plus, and then in this second term, we do have a y term, so our constant will come down, and then we'll take the derivative with respect to y, 3y squared. So f sub y, the second derivative, second partial derivative with respect to y and respect to y again, would be 72x cubed y squared. And then lastly, if we wanted to do f sub yx, we're going to take f sub y, which is this guy, and we're going to take the partial derivative with respect to x. So we're going to keep the y as a constant and let the x be the variable. So in the first term, 3x squared, that's just a regular derivative with respect to x, so 6x. And then this second part, the y is the constant, so plus 24y cubed. And then we'll take the derivative of x cubed, so that's 3x squared. So I have 6x plus 72y cubed x squared. And you will notice, and this is not a coincidence, that when you do f sub xy and f sub yx, you'll get the same exact thing. That's not a coincidence. That always happens. So if you know one, you get the other one for free. Okay, so that's just kind of a quick overview of partial derivatives. Let me do a couple challenging questions. So this first question, I had the forethought of writing down what it was, or grabbing that. So this is the prep for 13.3, and it's one of the later problems, 13.3.93, which, if you don't know, is a reference to the book of what problem this matches in the book. So now, traveling waves, for example, water waves or electromagnetic waves exhibit periodic motion in both time and position in one dimension. For example, a wave on a string. Wave motion is governed by the one-dimensional wave equation below, where u of xt is the height or displacement of the wave surface at position x and time t, and c is a constant speed of the wave. Show that uxt is a solution to this wave equation. So there's two things happening in this equation. This is what we're trying to see. Is this true when, and then we've got this equation, u of xt equals 6 cosine of 5 times x plus ct plus 7 sine of x minus ct. So what is this blue asking? This is saying the derivative of u with respect to t first, and then the derivative with respect to t again. So that's the d2u over dt2, and we can think of that as u sub tt. Now they want to know when my u of t is this function, is the partial derivative with respect to u, partial derivative of u with respect to t, and then the derivative of that with respect to t, is that the same as some number c squared, which is referencing these c's here, times the partial with respect to x of the partial of u with respect to x. So is u sub tt the same as c squared times u sub xx is the question. So now what we have to do is find u sub x and u sub t, and then find their second derivatives, u sub tt and u sub xx. So let's write down our function first. So our u function is 6 cosine of 5x plus ct plus 7 sine of x minus ct. So if I want u sub x, that means pretend t is a number, a fixed value. So u sub x is going to equal, let's see, 6 will come down. Now the derivative of cosine is negative sine. So I'm going to put the original inside in there. And now since it wasn't just cosine of x, in this case it was 5 times x plus ct, I have to use the chain rule to take the derivative of the inside function. So now remember, we're taking the derivative of 5 parentheses x plus ct, the derivative of this with respect to x. So that means the t and the c are constants. So the derivative of this constant would be 0, and then the derivative of this constant would be 1. So this would end up being 5 times 1. And now we have to do the next portion. So plus, the 7's going to come down. Now the derivative of sine is cosine, so cosine of x minus ct. And now since the inside, the thing I was originally taking sine of, is not just x, we have to times by its derivative. So we're thinking, what is the derivative of x minus ct with respect to x? So we're going to let c, be a constant, which it always is a constant, and then t also be constant or fixed. So the derivative of this guy is just 1, right? Because ct again goes to 0. So I'm timesing this guy by 1. So u sub xx, or sorry, u sub x. Oh, that marker's too fat, sorry. So u sub x is going to be, let's see, 6, negative, and 5 make negative 30 sine of 5 and then x plus ct plus, and then on this right-hand term, 7 times 1 is 7, so 7 cosine of x minus ct. Now, we weren't interested in just u sub x, we wanted u sub xx. So u sub xx is going to be the derivative of u sub x with respect to x. So we're taking the partial derivative with respect to x of what we just got for u sub x. So u sub xx will equal, so the negative 30 is going to come down. The derivative of sine is cosine, so you keep whatever was inside the cosine. But now, if that wasn't just x in this case, because x is what we're taking the derivative with respect to, then we also have to times by its derivative, which we decided was 5 times 1. And then on the next term, 7 cosine x minus ct, the 7 comes down. The derivative of cosine is negative sine. Sorry, I got to write that negative in there. Negative sine of x minus ct. And now, since it wasn't just originally cosine of x, we have to times by its derivative. And in orange, you can see that that derivative was 1. So u sub xx is, let's see, negative 30 times 5 makes negative 150 cosine of 5x plus ct, and then minus 7 sine of x minus ct. So this is my u sub xx. Now, we have to take that same u function, which I'm going to just zoom out and kind of copy. So let's restart with u equals 6 cosine of 5 parentheses x plus ct plus 7 sine of x minus ct. Okay, so now we've got another double derivative to take. We want u sub tt. So to start, we'll do u sub t. So that means pretend x is a number, just whatever number. It's fixed. So here, the first term, 6, and then the derivative of cosine is negative sine. And then we have to times by the derivative of the inside. Now, we're doing the derivative with respect to t of 5 times x plus ct. So, with respect to t, the derivative of x is 0, and the derivative of c times t is c. And we still have this 5 out here, so this makes 5c, and that's what I'm going to times by. Now, we'll do the second piece, so plus, the 7 comes down, the derivative of sine is cosine. And now we have to multiply by the derivative of the inside. And so that's with respect to t. So I'm doing the derivative with respect to t of x minus ct. So x is counted as a constant, so its derivative is 0. And then the derivative of minus ct, since t is our independent variable here, will just be negative c. So I'll put a negative c here. And now we'll just rewrite that, just clean it up a little bit. So I have u sub t is equal to, let's see, 6, negative, and 5c makes negative 30c sine of 5x plus ct. And then 7 times minus c is minus 7 cosine of, minus 7c, and then cosine of x minus ct. Okay, so this is u sub t, the partial derivative of u with respect to t, which keeps all the other variables as constants. Now we want to do that again. So now we want u sub tt, so the second derivative of u with respect to t again. And again, these are partial derivatives, but it's kind of a mouthful. So let's do it. So here, negative 30c just comes down. The derivative of sine is cosine. And since it wasn't just sine of t, it was sine of 5 times x minus ct. We have to times by its derivative, which again is up in orange, was 5c. And then minus 7c, and the derivative of cosine is negative sine x minus ct. And since it wasn't just t inside, we have to multiply by its derivative, which again, it was in pink, was minus c. So now, let's just clean this up. U sub tt equals negative 30c times 5c, so that's negative 150c squared times the cosine of 5x plus ct, and then minus 7c times minus c makes minus 7c squared sine of x minus ct. And now if you look at both of those, like we've finished taking the derivative, but if you look at both of the terms in this u sub tt, they both have a c squared, and I'm going to just take that out for a second. So c squared, and then I know they both technically have a minus, but I'm not exactly interested in that right now. So negative 150 cosine of 5x plus ct, and then minus 7 sine of x minus ct. So now the reason that I wrote it this way is because if we zoom out to like 300 hours ago, come on computer, you could do it. Check out u sub xx. U sub xx was minus 150 cosine x plus c, 5x plus ct minus 7 sine of x minus ct, and that's exactly this thing here. So it turns out that u sub tt is equal to c squared times u sub xx. And that's exactly what we wanted to prove here. So now, sorry, there's a trash can right outside my window, or not trash can, garbage truck. So now MathLab will have you answer like several intermediate questions to get to showing that this is true. I'm going to make a second video just because this video is so long. It's already 30 minutes for this next question, because this next question is also kind of long. So I'll see you in the next video.